Hey everybody, welcome to CS302 assignment 1, and in the assignment we can see right there we have Alan Turing, and he is, looks like he's developing a program to be executed on his famous Turing machine. So for us, we're going to, well, we're not going to have our program run on Turing machine, but Turing machines do have a lot of computing power as well as these modern machines. But anyway, let's get to the point. So for the assignment, we're going to be working on a linked list data structure, which the purpose of this is because it's a little bit of a recap from CS202. Whenever you took CS202, whether it was the previous semester or earlier, this is supposed to be designed to be a little bit of a warm-up into CS302. So obviously, the purpose is pretty clear. We're going to develop a linked list data structure, and the skills gained, well, obviously, we're going to learn several fundamentals, or these are the skills you will acquire when you complete the assignment. So memory management, because you have to dynamically allocate nodes for a linked list. Of course, pointers in C++ are to be used to implement this dynamic memory allocation. And of course, as always, we are doing C++, so always object-oriented design is always going to be needed because we'll have public and private members and all of that. And I guess the other skill to be gained, clearly, obviously, a linked list data structure along with iterators. So that's just the quick, just sort of intro to the assignment. Let's go ahead now discuss a little bit about the actual data structures themselves. Okay, so I'm going to first just do a quick rundown of the PDF and of the class structure, and then I will, of course, do some examples using OneNote to draw out how you want to visualize this data structure. Now, you notice that I switched on the right side of the screen. I switched up with the Sublime editor, and I know we use Visual Studio Code here at UNLV and CS, but I'm not a big fan of Visual Studio Code. I mean, it is a nice editor, and I do like to use it in certain cases, but really, whenever I do any basic programming, C++, terminal-based, command line, terminal-based programming, I rather use a simple editor with a terminal. And on my Windows machine, I do have WSL installed that runs Ubuntu, like in G++, and use GDB for debugger and so forth. Now, of course, if I do anything a bit more complex, then maybe an IDE is a better choice if you're doing like mobile or web. Especially mobile, you have Android Studio. Also, you do have Visual Studio is a nice IDE to do a lot of development as well. But for command line based, I'll just use Sublime. So I'm just gonna stop ranting about that and move on to the actual content. So you can read the PDF here, but I guess I'll show you the code here on the on editor. So right here, you may notice that we have these header guards right there at the very top. And the purpose behind a header guard is if in case we do multiple includes of the linked list header file, it's not going to cause any ambiguities when you're compiling your code. So this is not going to allow you to, if you do, let's say through multiple includes, if you do by accident include this header file multiple times, it's not going to allow you to override the previous include. So just a fail safe right there. Okay, so let's go ahead and go through our linked list class. So of course we have our struct node. Now of course I could have made it into a class instead of a struct, but really, sort of the convention is for a more complicated data structure, a class is more preferred, and of course for a more simple data structure, a struct. So really this node is a very simple data structure, so really a struct is good enough because everything by default is public, which makes it easier to work with this. So we have a set of nodes in our linked list. Each node will have a data field, a previous and next pointer, so it will be a doubly linked list. And we have a template sort of setup. And of course, you could have used template class instead of template type name, but anyway, it's going to be a template because remember, a linked list could be a linked list of integers, of doubles, or any type you want. And then we have this private member node star dummy. Now this is going to be a little bit tricky, so I think drawing the pictures out in a little bit will be helpful. So we're going to have a doubly linked list, as you can see, because our struct node has our previous and next pointers, but it's going to be a circular linked list, as in there's no head and tail pointer. We have a dummy node, which is going to symbolize we went beyond our linked list. But if we go beyond dummy, we wrap around back to the beginning of our linked list. So I'll draw a picture up, but this dummy node is going to represent really unofficially null in a way, but it will allow us to easily implement this circular quality. And also in main, we'll be able to denote if we reach beyond our linked list, because if our iterator equals dummy, then we went beyond our linked list, whether in the left to right direction or right to left direction. But anyway, I'll draw this up in a little bit. Now we have this class iterator, and so this header file, I actually give this to you. This is going to be given to you in the Canvas assignment section. And I give you the whole iterator class declaration, or not declaration, implementation, because really it's a very simple class, so it's not very complicated. But you notice that we defined a class iterator within the class linked list. And the reason is because, well, iterator by itself won't actually have any use. So without a linked list, there's no purpose of an iterator. So it makes sense to define iterator within this linked list. So the iterator is going to really just behave like really a more complex pointer, if you will. So remember from CS302, you use pointers to iterate through your linked list and access each node one by one. This iterator is going to allow you in main or in any scope outside of linked list, it will allow you to access, navigate the linked list like a pointer, but we keep the pointer content hidden. So in our class iterator, we have our node star current, which is going to essentially, for each iterator, we're going to sort of store which node it's pointing to. So whatever address is stored in current tells us the iterator which node it points to. Then we have, of course, a friend class linked list, and the purpose behind this is so if we were to define an iterator object locally inside of a linked list member function, we will have access to the private member current directly within the linked list class if needed. Now we have our two constructors. So our default constructor just sets current to null, and this constructor is going to set current to whatever address we pass into it. This operator star, this prefix operator we're going to overload, it just simply returns the data field of the node that this iterator points to. So the iterator contains a current field. That current pointer contains the address of which node it points to in the linked list, and this operator is going to return that node's data field. So it behaves similar to a dereference operator for iterator. Now our plus plus and minus minus operators, so we have essentially the prefix, or sorry, this will be the postfix operator, plus plus. This is going to be your prefix operator. So remember, postfix means that the plus plus appears after the variable, and prefix is where the plus plus appears before the variable. So we have two operators. Essentially, all the plus plus operator really does is going to move the iterator one element to the right in the current position of where the iterator points to. So as you can see here, the plus plus operator, we're going to update the current to assign it to point to the next node in the linked list, then return I. But for the prefix operator, we return star this because it's just a loop or a workaround, because remember, the plus plus postfix operator updates the variable after the statement has been completed. So remember, plus plus before the prefix version updates the variable first, then returns the updated version of the variable. So anyway, you won't have to use, typically, the postfix operator is going to be good enough, but I just have two versions of it if in case you want to use the pre or postfix. And for minus minus, same idea. You just basically just move the iterator to the left by one. So it's just a way to allow us to move iterators in our linked list. And of course, I'll show the picture so you can see what's going on. Then the comparison operators, we just simply compare two iterators. So if the this current equals the right-hand side's current, so if the two iterators point to the same node, it returns true. Else returns false, and not equals is essentially the opposite. So that's going to be our iterator class, but this header file will be given to you. And you don't want to mess with this because when you submit to CodeGrade, you're only going to submit one file, and this header file already will be included in the CodeGrade submission. It's going to link whatever is in CodeGrade to your implementation file. So don't mess with the header file, but just use these functions as needed. It's given to you, so it's just there. So you don't have to worry about implementing these, since I don't think in CS302 we go over iterators that much. So this is just really an object, but it behaves like a pointer. Then we have our linked list content. So we just first covered iterators, now covered a linked list class. So you first have our default constructor. This constructor is going to allocate a node to dummy. So dummy equals new node. And then we're going to set dummy arrow next and dummy arrow previous to both be null pointer. Because for the circular linked list, which I'll repeat in this video later on as well, dummy arrow next is always going to be the address of the head node, and dummy arrow previous, or prev, is going to always contain the address of your tail node. But I will repeat that several times in the video. So when we have our default constructor, we want to set dummies next and previous to both be null, which denotes that there's no actual node in a linked list. Dummy doesn't count as a node. Dummy node is just there to help us know when we hit the end of our linked list. So if dummy, next, and previous both equal null, that means we don't have any relevant data in our linked list. Okay, so now we have our copy constructor. Okay, I'll go into this file right here. So again, I also give you guys this file as well, and it's going to just contain, you have to fill in the blanks for these functions. So for the copy constructor, this constructor is also going to have to first set a dummy equals new node, and then set dummy next, dummy previous equal to null pointer, and then you have to traverse through every node of the copy object, and one by one you have to insert each node one by one into this linked list, and I'll let you sort of work on that. The equals operator is fairly similar to the copy constructor. The difference is you want to first check for self-reference, because this could, or for self-assignment, because this could actually happen when you're trying to assign two objects that are the same objects. Let's say you're trying to assign linked list 1 equals linked list 1. It's, there's no point doing anything at that point. So this checks for self-assignment. In the if statement, you can write your code right here. You're going to basically have to first deallocate the entire this linked list, except for the dummy node. You don't want to deallocate that. But everything except for dummy node, you want to first deallocate. And then you want to traverse through each node of your RHS object, and one by one, just deep copy everything into your this object. The destructor will deallocate the entire this linked list, including the dummy node as well, because once the destructor is called, the object is destroyed, so you want to deallocate every node and also deallocate dummy node as well, because you want to deallocate every single node in the linked list when the object goes out of scope. Now push front and pop front, these functions will be, so push front will be a head insert, pop front will be a head remove. So again, you want to be careful. You want to make sure you're aware of how to update this. There's really two cases to consider. So for push front, you want to consider the case when your list is empty. So you have one other node. So you want to consider when the case is empty. So if you only have just a dummy node in your linked list, so dummy arrow previous equals null, then then you have a different logic you have to apply in that case. If your linked list has at least one node, then you have a separate logic. So you have two cases. If your list is empty and if it's not empty, there's two different logic. Pop front also has the same idea. There's two different pieces of logic. You have a case where if you have only one node in your linked list, you want to deallocate that and then set dummies next, dummy previous to both be null, because if you had one node and you call pop front, your linked list now becomes empty. So you have a case again where if you have only one node, or if you have no nodes, you have those two cases to consider. Sorry, if you have one node, or if you have more than one node, my mistake. So if you have one node only, that'll be a separate logic than if you have more than one node. So, and then push back and pop back are very similar to pop front and push front. So just the opposite end of the list, but same logic, same cases you want to consider as well. Now, let me see, RemoveAtPosition. So this function, the iterator is going to, so iterator.current is going to point to a node in the linked list, this function is going to remove a node that the iterator points to. So just you want to deallocate something in between in the linked list. So after it deallocates that node, you want to set I to point to the next node from where it used to be. So if let's say if I points to, let's say, the second node in the linked list, after you deallocate a second node, you want to move it to the third node, because the third node is now going to be the new second node in the linked list, if that makes sense. And then after that, I give you a few other functions. So isEmpty returns true if the list is empty, and false otherwise. So this function can be used in your program to check if the list is empty. So if dummy next and dummy previous are both null, obviously that node's an empty linked list. Then you have the begin and end functions. So the begin function is going to return an iterator that points to the front node. So let's say if the list is not empty, I could have used isEmpty actually right here instead to make the logic a bit easier, but that's okay. So I first check if the list is empty, then return dummy node. If the list is not empty, it returns dummy arrow next, which means it's going to return an iterator whose current will contain dummy arrow next, which will be the address of your first node in the linked list. And the end function returns an iterator whose current contains dummy, which denotes the end of the linked list. So again, I have some sample code provided for you in these files, but I will also draw it out for you in the video as well soon. And then this function, swap nodes, that's going to be the more difficult function to write. So you're going to have two iterators, I and j, and you want to swap those nodes in the linked list. Now, you don't want to just only swap the two nodes data fields. You want to geographically swap the two nodes. You almost want to pick up one node and the other node and just sort of move them in the list. So we're not going to be swapping data fields. We're going to swap the entire node. So I will draw it out what that means, what the swap nodes will be used for. So this will be used heavily in the select and sort function that I pretty much give you. So let's go ahead now go over some of these sample files that are given to you, and then I'll go ahead and draw out sort of how you want to structure, these functions for the linked list class. Okay, so this is one of the main files that can be linked to your linked list.cap file, assuming that you have your code written correctly. But these are actually used to help, I guess, you can test out different components of your class, sort of little by little. So these are like kind of, I guess, unit tests in a way, but just mostly just testing out different parts of your code. So here, this file only tests out the push back and push front functions. So we have this Nickelodeon class. So you have a linked list of strings, and I push back several, I guess, known Nickelodeon cartoon characters. So wondering if anyone's able to identify which TV shows or which Nickelodeon cartoons these characters are from. Some of them are obvious, like SpongeBob, but some of these are definitely more 90s Nickelodeon, which those are pretty good cartoons as well back in the day. So right here, I would push SpongeBob to the back of the list, then I push back Doug, then I push Ickis in front of SpongeBob and Doug, then I push Rocco on to the end of our list, and I push Tommy to the front. So right here, I create two iterators, or I create iterator in a for loop. So the auto keyword allows me to create my data type, because really the actual data type for the iterator would look like this. It would be ll string and then oops, I can't spell, iterator. So that's the data type because iterator is the class type, but since iterator was defined within the linked list class, you have to first have a linked list, followed by a scope operator to enter linked list scope in order to access this public class definition or public class iterator. So auto is like a nice little keyword that automatically assigns iterator. So it is assigned to, well, Nickelodeon.begin. Remember, this begin function returns an iterator whose current points to the first node. So since this returns iterator object, it's going to be assigned to IT. IT's type will be whatever this is, but this returns iterator, so it's a little shortcut from writing out that entire data type. So we set IT to the beginning, while it's not equal to the end, IT++. It's going to one by one iterate through each node one at a time, and we just simply output by calling the start operator on the iterator and outputs the content in the node. Then also in this for loop right here, I go from right to left. I set the iterator to point to the end, but end returns a dummy node, so I have to minus that to point before the dummy node, which remember, the node before dummy will be your tail node. Remember, dummy arrow previous always points to your tail node, so IT points to that tail node. While it's not equal to the end, we just minus, and then once we hit the front node, if you minus once more from the front, we go to our dummy node. But again, later in the video, I'll show you the actual data structure sort of used, or how the linked list structure would look. So let's go ahead and compile this. So right here, as you can see, I include a header file and a CPP file as well. The reason why is because in C++ with templates, it has a very hard time linking. I tried to do my research in Google and just figure out how do I link a template class to a main. Now, one suggestion was to put all of this into the header file all in one place, but I don't want to do that because I want to have it where I don't want anybody to modify the header files, so I want to keep them separate, because on CodeGrade, I'm going to have a header file provided for you, and I don't want you to, if you try to mess with the header file, it will not work potentially on CodeGrade. So I'm trying to make it where you have to implement this class the way it's sort of structured right here. So the only loop around that I was able to find was you'd have to include both the header and implementation in the same file. Now to compile this, you just have to just say G++ and then ll insert.cpp. And it's going to compile and link to our linked list CPP file, which, I mean, it's not going to be this one. This one is an empty one, but I'm using the one that, that I already have written. If I go ahead and run this, there's the output. So the iterator just one by one goes to each node one by one through the linked list. And the same thing for the other files as well. So for ll RemoveAtPosition, same thing is provided for you. If you want to compile this, you just do G++ ll remove.cpp, and it runs the code like that. So I do provide also the outputs along with these test mains as well. I also have them going to be included as well in the Canvas assignment section. But just to show you, that's how you would compile all of this. And for the selection sort that I give everybody, this is going to implement a very simple sorting algorithm, but again, I give this to you. So I also give you the input files as well. So if you want to compile this, all you'd have to do is G++ selection sort.cpp, and then run it. We do a.out. And there's actually the input provided is going to be used. We're going to be using Linux redirection to input. So I have also i1.txt. I provide you with i1, i2, i3, which will be 3 different input files, which will contain some kind of unsorted array in each of these. And this is going to read in this file, and it's going to output the array sorted. So if it doesn't output it sorted in your case, it didn't work. So this code does work. So, but again, it depends on your pushbacks and content has to work. But the most important function really is your swap nodes function is going to be used quite heavily in this selection sort. But I also provide you several other main files that will test out different components. It's a deep copy test, the swap test we also do as well, and so forth. So that's sort of how you would compile the code, a quick rundown of the files given to you. Now let's go ahead and go over the last part, which will be the visualization of how this linked list class would look like. Okay, so let's first go ahead and I'm going to write the code as you would write in main, and I'm going to also at the same time sort of go over how the object internally would look like. So I'm going to use just the class object Nick, or not Nickelodeon, but Nick is short for Nickelodeon. So when we use the constructor, what's going to happen is we're going to have this dummy node, which is a member of the linked list class. The constructor is going to just basically allocate this node, and I'll just move this over here like that. And then of course dummy would point to it. It's a very simple setup. Remember, each node has these 3 fields. Actually, I should probably use the arrow object as well. There we are. So let me just go ahead and just put these over here as well. This looks a bit nicer. And for our default constructor, we're going to set these, the previous and next fields to both be null, just like that. Okay, so suppose now, let's go ahead and go over, I guess, push front. So I think I discussed that a little bit earlier in the video, so I'll go over push front. Now, push back is actually very similar, just sort of on the opposite end of the list. So really, the same logic will be used. So suppose I decide to do Nick dot push front Doug. Now, Doug was definitely a great TV show. It was really, I think, the show that really encapsulated how introverts are like. And of course, you had to really love the acapella. Sometimes, the little songs they would play during the show, they had used acapella sometimes, which is definitely added a little extra to that show, I think. So anyway, let me go ahead and sort of copy this and bring it down here. Hopefully it didn't mess up my entire OneNote with this copying. Let's see. It didn't mess anything up. Okay, great. So when we want to do a push front Doug, remember this dummy node is going to be, I guess I'll put it at the end for right now. But what's going to happen is in this function, we first check. So right now our linked list is empty because even though we have this dummy node, yes, but if you only have just a dummy node in our linked list, it means we don't have any actual nodes in the linked list. So what we're going to have to do is, of course, no matter what, we have to allocate a node regardless. I'll just call it temp for right now. Call it anything you like. I mean, you can call it anything, but I'll just call it temp. I think I can't really fit Doug in here, so I'm gonna have to like be a little bit creative right now in this, but the data field, I think I'll move it like this. So I'll make it to a different looking node. So there we go. I'm gonna write Doug right here. Perfect. So we're gonna insert Doug right there. Now, in this case right here, since we have only one node in our linked list, well, this temp node's next will obviously have to point to dummy, and dummy will point back to it. Because, well, this is going to be our front and back node simultaneously. I'm going to try to see if I can figure this out. So the temp is going to, temp's previous will point back to dummy. And dummy's next will point to Doug. So you can see how it is rather circular. And of course, after the function is done, temp was a temporary variable defined locally in the function body. So then we're left off with that. So that's going to be the end of push front in this particular case. Let's do one more example of a case where we call push front on a scenario when we have at least one node. So I hope this drawing kind of helped you do this, but a linked list really is a very step-by-step structure. So each arrow update was just simply overriding. So I was setting temp arrow next equal to dummy, to dummy arrow previous equal temp. So I was doing just a lot of those pointer reassignments. All I did to update each of these arrows to point elsewhere. Remember, the dummy's previous always points to the end node, and dummy arrow next always points to the front node. Now in this case, since Doug is only one node by itself, it's both the front and back. Okay, let's go ahead and now I'm going to copy this so I can just have to redraw it to make the video a little shorter. Although this writing pad has issues at highlighting this, has issues highlighting stuff for some reason. There we go. So Control C. Okay. So suppose I want to do one more push front. So I'm going to say Nick dot push front. And I guess I'm going to go ahead and use the same cartoon. So I'm going to say Roger Klotz from Doug. So we have the current list right here. So let me just go ahead and just scroll up a little bit. I'm going to go ahead and I'm going to paste. So here's our current status of our, I'll move this over a little bit to the right. Here we go. Here's our current status of our linked list right here. So in this case, we can tell our list is not empty. We have at least one element because since dummy arrow next and dummy arrow previous are not both null, we have at least one node in our linked list. So really, we have two cases to consider if we have an empty linked list or we don't have an empty linked list. So this case is not empty. So no matter what, however, we have to allocate a new node either way. So I'm going to just here's our new node I'm going to allocate. This will be temp. And then I'm going to set the, sorry, I'm going to use the arrow object to make a nice looking linked list, or nice looking node, sorry. And I'll fit Roger right in here. Perfect. There we are. So we have to insert to the front of our linked list. So right now, Doug used to be the front of our linked list, but now it's not going to be the front node. So what's going to happen is Doug's previous has to point back to Roger because, well, it's doubly linked list. So Doug has to point back because Doug won't be the first node anymore. Doug is our second node in our linked list. So we have to update Doug to point to this temp node. So we have to just set this node. So we have to first get the address of this node. Once we have the address of it, we can get it by just saying dummy arrow next. That's going to contain the address of that node Doug. Now that we have that node, we can dereference it once again, access the previous field and set it to temp, which will set Doug's previous point to Roger. And then we can, of course, set Roger's next to point to Doug by very easily, because since temp, we already have the address of Roger because temp points to it. And we have the address of Doug because, well, dummy arrow next is always going to point to the current head node. So very easy to access Doug and Roger. And we just set these to point to each other. And then what we have to do is, since temp is going to be my new front node, well, anything to the left of the head node is going to be, the end of our linked list. So we have to set temp's previous to point to dummy, because anything to the left of the head node is going to point to an invalid. It's going to fall off the linked list, basically. So we have to make sure that the front node's previous always points to, in this case, to dummy. And then dummy arrow next has to be reassigned to point to temp, because temp is my new front node. As you can see, now Roger is our front node, Doug is our second node, and then dummy is the node after the tail, and also the node before the head. So Roger is your head node, so the node before Roger is dummy, the node after Doug is dummy, because after Doug there's no more nodes, and before Roger there's no node. So it's going to be dummy represents kind of like the end, essentially. And then of course temp is going to go away once you finish your function because temp is locally defined. You can see here, if we do dummy arrow previous, we point to our end node, and dummy arrow next points to our front node. So really we have to consider those two cases. If I were to run the same code again on this example, it would still work the same way because, well, you have only two cases to consider. Either our list is empty when we try to push front, or it's not empty when we try to push front. Let's go ahead and now go over pop front next. Okay, so let's go ahead and go over pop front, which is going to be our head removal. Now again, pop back will be similar, except just on the opposite end of the linked list. So again, pop front and even pop back have the same cases to consider. So if you have only one node in a linked list, or if you have more than one node, you have two separate conditions to check for. So in this case, how do we actually know by code? So obviously we can look at this linked list. Oh yeah, clearly there's two nodes, Roger and Doug. But how can we by code be able to verify this? Well, it's actually easy, because if you only have one node, then dummy next and dummy previous would point to the same node. If that's the case, then we know we only have one node in our linked list. Of course, we could iterate through the whole linked list and have a counter. If the counter equals 1, then we have only one node. But yeah, that requires us to iterate through the whole linked list. It seems like it's much more efficient to not have to loop through the linked list, just be able to quickly look at just dummies, next, and previous pointers and check if they're the same exact node. If they are, then it's going to be only one node. But here in this case, clearly, dummy arrow previous refers to Doug, and dummy arrow next, so this is your previous field right there, and dummy arrow next refers to Roger. So they're two separate nodes, therefore, okay, well, we know we have at least, more than one node in our linked list, so we're gonna run one of our cases. So in this case, so I think I'll write the code right here. I'll just put this here actually. So Nick dot pop front. I believe I already copied that linked list already, so I can just paste it right here. I can, of course, just sort of mess around with this list. So let me just move this over here. Okay, that's good. So we verify that we have at least more than one node in our linked list. So we have to delete or remove our front node. So clearly, dummy arrow next refers to this node Roger. So we have to remove Roger from our linked list. So first thing we have, I guess we can do is we can set a pointer. I mean, I'd recommend just doing this actually. You can create some temporary pointer that points to that front node. So head in this case is not an instance variable in the linked list class. Head could be considered to be a local variable defined in the pop front function. And we can just set head equal to dummy arrow next. So we have our head pointer, which is going to be nice to use this pointer to help us with this pop front. So the first thing we have to do is, well, obvious ones. We just have to just basically set this dummy next to now point to Doug. And that was easy because head arrow next contains the address of our next node. So the node after Doug is going to be our new front node from this point on. So you want to, of course, set our dummy arrow next to point to that front node. Okay, and after that, what we're going to have to do is, Doug arrow previous. So since this node is going to be the new front node, the previous node, the node to the left of Doug, can no longer be Roger. Instead, it has to be the dummy node. So that's also an easy check. Because we know the address of dummy, we can just set, this node right here. We have the address of it. We can, of course, make another pointer if you wanted to. You can create another pointer, head 2 that points this node if you want to as well, but I'll leave that open for you. But we have the address of Doug, so we can easily just reassign Doug to point to dummy. And then we just have to just deallocate our head pointer. And if we do that, this node is now deallocated, so it's going to just disappear basically. And what's left is that linked list right there. We can see that now we had Roger in the front, but we removed Roger. The node that came after Roger, that was the second node. But if we delete our head node, then our second node becomes our new head node. So that's going to be that case. Now, if I were to, let me go ahead and just sort of copy this down once more to make it easier. Let's call pop front once again on this example. So let me just paste this. I'm going to write over here. So suppose we want to do Nickelodeon or Nick.pop front. Once again, I'm going to paste that image right here. There we are. Okay. So we call pop front again on this current linked list right here. So in this case, well, we can tell that we only have one node in our linked list. And it's clear because, well, dummy arrow next and dummy arrow previous both point to the same node. So we can see here, dummy arrow previous, which is our tail node, and dummy arrow next, which is the head pointer, they point to the same node, Doug, which means we know we only have one node in this linked list. In this case, it's a very easy scenario. We just have to just deallocate this and then just set these 2 pointers for dummy to both be null. And then, of course, we deallocate Doug, disappears basically, and we're left with that. So a very simple case to check for. But remember, always remember a dummy arrow next is always the head node, dummy arrow previous is your tail node, and feel free to actually create additional temporary pointers in your functions to help you. So you could say dummy arrow next, arrow previous. You can do all that stuff, but it's easier to set maybe a pointer. You can just set a pointer node star head equal to dummy arrow next, and then using the head pointer you can manipulate your linked list. So you makes it a bit more simpler to work out the details. But anyway, that was the push front, pop front functionality. So let's go ahead now, just talk about how iterators work with our linked list class, and then get into the remove function and the swap functions. Okay, so let's consider the following linked list right here. And I'm not going to really focus on the data fields because those are really irrelevant for this example right here. So suppose we did a bunch of pushbacks and push fronts, and we have this linked list right here created. And notice we have our dummy node right there. So really, this node will be our front node because if you look at our linked list, dummy arrow next is going to be this pointer right there, which essentially points to that front node. That's going to be your front node. So dummy arrow next always points to the front. And you also can notice that dummy arrow previous is going to be this pointer right there, which refers to that node. So that's going to be your end node. So again, it's consistent around that idea. Oops, I moved too much right there. It's hard to actually move a little small piece. There we go. So right here at the very bottom of this OneNote page, you'll notice that we have this auto IT. I use auto because I don't want to have to write out the write the entire thing out. But I guess I think on some of the test mains, I actually do write out linked list, sort of angle brackets, data type, followed by a scope operator, iterator. But auto just kind of saves me some time right here to write this out. So remember, the begin function is going to return an iterator whose current points to the first node. So right here in our example, dummy arrow next contains the address of that node. So the begin function is going to return an iterator whose current points to that node. So when you're going to assign it to IT, so IT is drawn right here as an object, what's going to happen is it's going to set IT's current to point to that front node right there. Because the begin function returns an iterator, and this is going to just use the assignment operator. It's going to shallow copy IT with the begin function's result. So IT will point to current. It's a shallow copy, but that's good enough. We want that because we want to have iterator point to that first node. So if I were to go ahead and I were to say something like, cout star IT and L, this star operator is going to call the iterators overload star operator, and it's going to return the data field of that node that IT points to. And right here, I'm not really highlighting the actual data fields. If it contains some data, it would return that right now. Okay, so, iterators are very similar to pointers. Let's go ahead and do the following. I'll try to move this down a little bit. So I think I have to hit Control Shift, I believe. There we go. So if I were to do something like either, if I were to do plus plus IT, or if I did IT plus plus, either one will do the same thing. The plus plus operator is going to simply move iterator, so IT's current field will be set. So it will set IT's current equal to current arrow next. So it's going to set IT's current to point to the next node. So essentially, IT now points to the next node over. So I'm going to stick to plus plus IT instead, but either one of those two will work. It will just move iterator over to the next node. And if I do plus plus again, it moves it over once more. If I do minus minus IT, it'll move it to the left position. So again, those operators are written for you, but they work just like that. So you can see here, it's a very nice way for it to actually, nice way to maneuver through your linked list. Now, also, if I want to set the IT to point to the last node, what you can do is we can do the following. I can say IT equals Nick dot end. If I want to do minus minus, actually, I'll write this out again. Minus minus Nick dot end. Now I apply this because, well, if I call the end function for the iterator, what's going to happen is that it's going to return an iterator that points to dummy, which it does, but we want to actually move it to the left. So I say nick.end, it returns the dummy node, or the iterator that points to dummy. If I minus minus that, it will set it to the node to the left of dummy, which is this node right here. So IT will be assigned to this node. If I take the end minus minus, the end function returns the iterator points to that node. Minus minusing it will move it over to the left, and the node to the left of dummy will be your end node. So you can see how iterators work. So let's go ahead. I'm going to move this over to the left a few times. I'm going to say maybe IT minus minus and IT minus minus again, which will just simply move iterator over to the left 2 times. So the first IT minus minus moves it over here. And next one, and after that, minus minus once more, we'll move it right there. So there we are. So now let's go ahead and go over the function RemoveAtPosition. So I believe it looks like this. You'd have to say, you have your Nick object dot remove at position. Oops, yeah, I think that's spelled correctly. I pass in the iterator. So I want to remove the node that IT points to. So in this example right here, let me just go back up into our picture. We want to essentially deallocate this node, but we first have to do the following. So remember how from 202 how this works. So the nodes that surround IT. So this node, actually I'll try to draw a nicer arrow. So this node and this node surround IT. So of course, feel free to allocate a few temporary helper pointers to help you with this. But all you have to do right here, just like from 202, you just need to do this. Set this pointer to point over here. Set this pointer, set this node, sorry, to point over there. And then you want to deallocate this node. And then the result is this node will disappear like that. And then IT.current really points nowhere. So you want to just set IT's current to then point to this node. So earlier, if you recall, this was our second node in the linked list, right? So IT used to point to our second node. But after we removed it, this node right here is now, I'll circle it, this node right here is now our second node, is our new second node. It was our third node before, but because we removed our second node, that third node is now our new second node. So we just set the IT to point to that node, so it still points to the same geographic location, or maybe the wrong words, but it still points to the correct node, if you will, the second node. It still points to the second node of the list after it finished. So anyway, that's the result of this delete. So you just simply create you create two local pointers in the function as helpers, which you have to just have to link the neighbors to jump over the node IT current points to, and then you have it, and you deallocate that node, and you're done. Now, the only edge cases to worry about here is what if IT points to the front or to the back? Well, if IT points to the front, then you can just simply call pop front. If IT points to the back, you can just call pop back. And then when you're done with that, so let's say if IT points to the front, after you call pop front, then you want to set IT to point to your new head node. And if IT was pointing to the end of your linked list, you can call pop back, and then you want to set IT current to point to your new end node. So you have to consider those edge cases as well if IT points to the front or to the back. But what I covered right now was the more the non edge case version. So you have to also consider the edge case, but it's not so bad because you can use pop front or pop back if they are written correctly. You can use those actually right here to simplify your code a little bit. So of course, try to reuse some of the functions when necessary rather than copy and pasting code throughout your program. So the last thing I'm going to cover is going to be the more difficult function, which will be the swap nodes function. Let's go ahead and discuss that now. Okay, so the swap nodes function. Now I drew this linked list without all the arrows right here because if I did, this is going to create a lot of chaos if I try to draw this out step by step. It will almost look like, if you remember from SpongeBob, where Mr. Krabs was trying to go on a date with Mrs. Puff, and you know when when Mr. Krabs says, "We're not talking about this or this, we're talking about this," like he draws these shapes, and then SpongeBob in the episode later on goes nuts, and he like draws a bunch of crazy shapes all over the screen. So if you remember that episode, it would look like that if I tried to draw the arrows and show you how this swap nodes would work. So for now, I'm going to keep the arrows out of here. And then, of course, you can kind of imagine how you would do this. So for this function, there really are, I guess, from what I remember, there was actually two edge cases to consider. If I and j were adjacent nodes, and if they were not adjacent nodes, were two scenarios. So here's a case where I and j are not adjacent. When they are adjacent to each other, it's actually an easier case. So I'll cover this case right here. So the easy way of doing a swap nodes would be just, well, okay, just take whatever's in I data and j data, swap those two, and you're done. But actually, it turns out doing that way is not very efficient. Now, of course, if each node contains a very simple type like integers and so forth, then it wouldn't be so bad. But consider a case, what if each node contained bigger amounts of data? Then doing that copying or swapping data fields does in fact have an overhead, especially if, let's say, data fields contain vectors or something. Then copying one vector to the other and swapping vectors over would be an overhead actually. So the simpler or more efficient way is this. You want to emulate this. We're going to take this node right here, pick it up or pick it down, sorry. Take that node right there, oops. Put that here, and put that here like that. So we're going to physically pick up the node I and j, physically pick them up, and then swap their locations in the linked list is what we're trying to actually do. Now I know this visualization was actually very simple, but there's actually a lot more that goes into it. Let me go ahead and sort of put these, hopefully this will go back to where it used to be. Perfect. So what you would have to do is, well, you have to, of course, I mean, it's up to you how you want to do this, but one simple way is you want to have really, you know, these pointers, like you want to have this pointer right here, this pointer right here, and you want to have really, I guess, two pointers. Now, again, this is a special case, but it still works out. I tested it, so it still works out actually. So the idea is you want to have one pointer to the left of I, one to the right of I, then one to the left of J, one to the right of J. Then you have to do a bunch of pointer reassignments. So you have to essentially do this, this does that, and then this goes over here, that goes over there. I don't want to draw the whole thing out, and I'll draw it out. I'll do the best I can. Then of course, this node points over here. This one points back over there. This points over here. This points over there, and voila, there we go. We have it. We have it all swapped. Very hideous picture. But you have to, of course, reassign these next and previous pointers to emulate that movement, because you want to essentially have it where I will physically go where J used to be, and then J will physically go where I used to be, is what you actually want to do. But again, it's really just a bunch of pointer reassignments, but you want to, of course, maybe just like this, draw it out first and make sure you have an idea of how you would do this. You don't want to just start coding this willy-nilly and hope for something to come out. But you have to do all those pointer assignments. So you want J's node to the left of J, you want its next to point to I, and I should point back to that node to the left of J. And then, of course, the node after J, you want it to point back to I, and I points to it. So, hopefully that gives you an idea of how you want to do that, but that's what you want to do. End of the day, what will happen is you're going to just swap these two nodes over like that. And after you do that, after you successfully swap these, then you want to swap the addresses of I and J, because after you do your swap, you still want I to still point. In this case, I was, it used to point to the second node in the list, and J was a fourth. And right now, I is actually the fourth node, not the second. So after you do this, you want to then swap the addresses, J's current with I's current, so that way I still points to the second node after swapping, and J still points to the fourth node, but it'll be a different node, but it's still the fourth node. So that's how you want to do a swap node. And then for the adjacent case, it's actually a bit easier, but similar concept. You have to essentially adjust I currents previous and next, and J current previous and next, and you have to, of course, update the nodes to the left of I and the right of J, update their next and previouses to emulate that movement, essentially. So that was basically the swap nodes function. So hopefully this explanation gave you an idea of how it works. But again, from what I tested out, the only edge cases, only two cases to consider when I and J were adjacent and when they're not adjacent. Those are only two cases to consider. And when I considered those two cases only, in my end, it did actually work. So I tested it out and it worked. So I'll just say that those are the two cases you want to check for. Let's go ahead and now just summarize and wrap up the assignment. Okay, so as mentioned before, I give you all of the main files that you can use to compile, and all you have to do is, if you wanted to test out a particular main, just G++ and then just give it the correct main you want to use. So it could be selection sort, LL insert, LL remove. So you have several main files you can use, and to compile it, you just do it like that. And on code grade, just to sort of show you this, here's a rubric for our first assignment. So we have our linked list class test, which is basically going to test out, well, it's going to just test your linked list class out. So it's going to sort of take your files. So you have to only just submit one single file, which will be the ll.cpp file, and that's it. The header file and all the mains, everything will be already in code grade. It will link those mains to your linked list.cpp file. So the auto test will just simply take all those mains and it will compile and run them, and it will compare them for the output. Then it also will val grind each of those mains for memory leaks in your program. Now the commenting documentation, as always, is in the PDF to have your code nice documented. you want to document your program, and the grader is going to manually enter the grade for the comments. So you want to have a header comment, just like in 135 and 202, where you had to document your code nicely. So you want to, of course, at the top of your ll.cpp, just have like your name, your student ID, and all that stuff, just like in 135 and 202, same idea. And then you want to comment all your functions in your ll.cpp file. So you want to have like the function name, the parameters, the return type, and description of what each function does. So really, just like the same method you did in CS202, same idea. So of course, when you submit your single file, it just will test it out, and it will just sort of, you can see here, it compiles it to different mains, and it runs it, compares the outputs, and it will check memory leaks with all your programs as well. So this is my example that I submitted, and it, of course, I had to make sure that it works on CodeGrade before you create the assignments. Anyway, there it is. So anyway, that's all for the video. Hopefully it did help you out, and happy coding.